Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate in the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you had any problems with homework or tutoring, then check out the links in the description below. So now we're just going to get started on the first set of questions. Okay, so question number 1. If you put 120 volts of electricity through a pickle, the pickle will smoke and start glowing an orange-yellow color. The light is emitted because the sodium ions in the pickle become excited, and then they return to the ground state, resulting in light emission. Question 1a. The wavelength of this emitted light is 589 nanometers. Calculate its frequency. B. What is the energy of 0.1 mole of these photons? C. Calculate the energy gap between the excited and ground states for the sodium ion. And then for D, if you soak the pickle for a long time in a different salt solution, such as strontium chloride, would you still observe 589 nanometer light emission? Why or why not? Okay, so that's kind of a cool question. So let's try to answer part A. The wavelength of this emitted light is 589 nanometers. So let me just write that down. And then from here, I'm going to convert from nanometers to meters. And I'll explain why in a bit. So it becomes 5.89 times 10 to the negative 7 meters. And the reason I did that is because I'm going to use this equation to calculate for frequency. C equals frequency times wavelength, where C is the speed of light. So let me just rewrite this equation that we're looking for frequency. And then the reason I wanted to convert from nanometers to meters is because the speed of light constant is in meters per second. So if I plug all my values in, the speed of light is 3 times 10 to the 8 meters per second. And then our wavelength is the 5.89 times 10 to the negative 7 meters. And then you'll notice that the units for meters cancels out. And then we're left with a final frequency value of 5.09 times 10 to the 14 1 over S, which is also the same thing as hertz. Okay, so that's part A. Part B asks, what is the energy of 0.1 mole of these photons? So for this question, to calculate for energy, it's going to be Planck's constant times F, which is what we calculated in the other question. But if you wanted to see what this equation looked like if we didn't calculate for it, it would be energy equals Planck's constant times the speed of light over wavelength. But in our case, we're lucky since we know the value for frequency. Now we just have to plug in Planck's constant, which is 6.626 times 10 to the negative 34. And its units are in joules times seconds. And then once we plug in the frequency, which is 5.09 times 10 to the 14, 1 over seconds, you'll notice that our seconds cancel out. And then we are left with an energy value of 20,323 joules. Or we can convert this to kilojoules just to make it a little clearer. 20.3 kilojoules. And then this is per photon. The question asks, what is the energy of 0.1 mole of these photons? So all we have to do is multiply this value first by Avogadro's number and then by the number of moles. So let me just write this down. Energy of 0.1 mole is equal to, oh, sorry. I skipped ahead a little bit. Let me just rewrite the actual answer for this. Okay, so multiplying Planck's constant by frequency will actually give you 3.37 times 10 to the negative 19. And then this is in joules per photon. So let me write that down here. We have our 3.37 times 10 to the negative 19 joules per photon. And then I'm going to multiply by Avogadro's number. So every time you have like moles involved and they want to find out how many particles, or if you have the number of particles or photons and you want to convert to moles, you know you want to use Avogadro's number. And the units for this is photons per mole. And then I'm going to multiply by 0.1 moles. Then you notice the photons cancel out, and then the moles cancel out. And then you get 20,323 joules, or 20.3 kilojoules. And then this is the answer for part B. Okay, now for C. Calculate the energy gap between the excited and ground states for the sodium ion. So we actually this is actually our answer that we got here, which is the 3.37 times 10 to the negative 19 joules per photon. So this is the energy gap between the excited state and the ground states for the sodium ion. And then part D asks, if you soak the pickle for a long time in a different salt solution, such as strontium chloride, would you still observe 589 nanometers light emission? Why or why not? So the answer for this is no, you would not. And that is because the energy gap between the ground state and the excited state of strontium will be different. Okay, so each element will have like a different energy gap since they all have different numbers of photons. And then let's check out the answer from our junior tutor. They said the speed of light equals frequency times wavelength, and then they calculated frequency to be 5.09 times 10 to the 14 hertz. B, they also got 20.3 kilojoules. For C, they had the 3.37 times 10 to the 19 joules per photon. And then they also converted to EV, which I didn't do, but it's still correct. And then no, because the gap between excited and ground states is dependent on the ions available. Sodium has a 509 emission, but strontium does not necessarily have a 589 emission either. The emission spectra is dependent on the nuclear charge of the species. So this solution was well written. It is correct. So solution is correct. Okay, so now we can move on to question number 2. There are 3 different possible isomers of a dibromoethene molecule C2H2Br2. One of them has no net dipole moment, but the other 2 do. Draw Lewis structures for each of these isomers, include hydrogen atoms. Okay, so this is question number 2. And then we're looking for all the different isomers of C2H2Br2. And then they separated it from nonpolar and polar. So I'm just going to write the definition of nonpolar. There is no dipole moment present in the molecule. And then for polar, there's a non-zero dipole moment. Okay, so for C2H2Br2, I'm going to write down the molecule for the nonpolar isomer. So this contains a double bond, and it contains 2 bromines and 2 hydrogens. But in order to not have a dipole moment, I'm going to make sure I write my bromine on the opposite end of the other bromine, and I'm going to make sure my hydrogens are also on the opposite ends. So you'll notice that these dipole moments cancel each other out. Let me write it in a different color. So bromine is an electronegative molecule, but you'll see that these cancel each other out. So therefore we have no dipole moment. And then the name of this compound is trans 1,2-dibromoethene. Okay, so ene comes from the double bond, and then dibromo means that there's two bromines, and then the 1, 2 shows which carbons contain the bromines, and then trans means that they are on opposite ends. So now I'm going to draw out the cis version of this molecule. So we're going to do the same thing, except this time I'm going to put our hydrogens on the same side. And now I'm going to put our bromines on the same side as well. And you'll notice that there is a non-zero dipole moment in the direction of the bromines. So they aren't canceling each other out or anything because they are on the same side. And then the name for this is easy. It's just the same as the other, except it is cis. So it's cis 1,2 dibromoethene. Okay, so I'm going to draw the last molecule that is also polar. Also contains a double bond, but this time looks like this, where the bromines are actually on the same carbon. So this is 1,1 dibromoethene. And you'll notice it also has a non-zero dipole moment going in the direction of the bromines. Okay, so let me write down some definitions here. So cis and trans are stereoisomers. So basically they have the same molecular formula, but they differ in orientation of the atoms. Okay, so I'm also going to write down the definition for a structural or constitutional isomer. This is when the molecular formula is the same. But they have different atom arrangements. Formula. Okay, so let's look at the answer of our junior tutor. Looks like they wrote... Okay. So they just put their 1,1 dipromoethene on the nonpolar side, but it should be switched with the trans. So I'm just going to correct that. But all of the structures are correct. Okay, so let me write this down. Okay, so I said that their structures are correct, but the trans 1,2-dibromoethene is nonpolar. And then I said the cis 1,2-dibromoethene and 1,1-dibromoethene are polar. Okay, so now I will move on to question number 3. For each compound, select all that apply. And basically we have like conjugated, non-conjugated, diene, or triene. Okay, so this is question number 3. And I'm going to look at A. So we have a double bond here. And then we have a triple bond at the end. So for here, 2 multiple bonds. Are separated by 1 carbon-carbon single bond. So therefore, for this compound, it is conjugated. Okay, so let's look at compound number B. You'll see we have 3 double bonds, all separated by 1 carbon-carbon single bond. So this compound is also conjugated. But I can also say that it is a triene. That means there are 3 double bonds. Okay, so now let's look at compound number C. We have a triple bonded carbon here, single bond, another single bond, and then another triply bonded carbon. So this is an example of a non-conjugated compound. And that's because there are 2 carbon-carbon single bonds in between the 2 triple bonds. So therefore, this is non-conjugated. And then lastly, let's look at D. I have a double bond here, 1 carbon-carbon single bond. And then there is a ketone up there. So therefore, this is also conjugated. So let's look at the answer from our junior tutor. Conjugated, conjugated and triene, non-conjugated, conjugated. Remember, conjugated refers to every other bond regardless if it's a double or triple bond, and dienes and trienes only go with C to C bonds. So this solution is correct. Okay, so let us move on to question number 4. Change the color of this. Amylose and amylopectin are the principal storage polysaccharides of 1. mollusks, 2. plants, 3. bacteria, 4. animals, or 5. insects. Okay, so I'm just I'm gonna go ahead and say that the answer for this question is that they are examples of the principal storage of polysaccharides in plants. It's gonna give a brief definition of amylose. So this is an example of soluble starch in plants. And then for amylopectin, this is the insoluble starch. So let's see what our junior tutor said about this question. Amylose, soluble starch. Yeah, they said it was plants. Soluble in hot water and used for starching clothing. A long molecule composed of 200 to 1,000 glucose subunits forming an unbranched helix. Interesting. Amylopectin is insoluble starch, shorter molecules than amylose with only 40 to 60 glucose subunits, forming highly branched chains that do not coil. Starch is deposited in concentric layers within the starch grains or amyloplasts. Starch grains of different plant species have characteristic shapes such as maize, corn, oats, bananas, potatoes, and wheat. For example, banana starch grains are more elongated than potato starch grains. The starch is hydrolyzed, broken down by amylase enzymes, and then during hydrolysis, a water molecule is inserted between each glucose subunit. So starch is then stored in underground organs, including storage roots, rhizomes, tubers, corms, and bulbs. So the starch granules contain two types of structures, the amylose and amylopectin, and then the amylose is shorter but far greater in number than amylopectin. Amylomase has around 50% amylose residues compared to waxy maize, which has mainly amylopectin and less than 3% amylose content. Also, the percentage of branching varies with plants. So that was a very nice and detailed explanation of the two different starches found in plants. So I'm just going to say that this solution is correct. Okay, so looks like my camera died, but maybe I can try to fix this. Before moving on to the next question. Give me 1 second. Okay, I just had to change the battery for that. I am back online. And now we can check out question number 5. Select the best reagent that will promote the following transformation. So here, we have the R configuration. Of this. And then we're looking for a reagent to convert it to the S conformation. And you'll also notice that there is now an N3 group there instead. So the reagent that we need for this transformation is this? Sodium azide, I believe. And DMF is just the solvent for it. So basically, I'll just write out my reasoning behind this. So when you have a configuration of product, so when it is inverted, like going from the R to the S, you know that an SN2 reaction was involved. So when you have polar protic solvents, so an example of this would be the methanol that they gave us in the question. This only favors SN1. On the other hand, when you have polar aprotic solvents, in this case it is DMF, or it could also be like DMSO or ether, then this favors SN2. So now we know that we can rule out the methanol in the two options. So now we're just looking at sodium versus iodine. So for this reaction in particular, we need a good nucleophile. So that's why we chose NaN3. So this is option A. Let's check out the answer from our junior tutor. In this substitution reaction, the configuration of the product is inverted, so it must be SN2, yep. Polar protic, like alcohols, favors SN1, in which ionization takes place, and then the polar aprotic solvents, such as DMSO, SMF, ether, favors SN2. So from the given options A and C, at the polar aprotic solvent DMF, for these SN2 reactions, we need a good nucleophile, yep. So when you compare the sodium is a good source for the azide ion. So for this conversion, the best reagent is the sodium azide and DMF. Great. So this solution is correct. Okay, so let's move on to question number 6. So it says, which of the below molecules will have an odd numbered molecular ion? Okay, so this is question 6. So first, before answering this question, I'm going to write down the nitrogen rule. And basically what this means is that if the mass of the compound is even, then we have an even number of nitrogens. Then, on the other hand, if the mass is odd, then we have an odd number of nitrogen. And the reason for this is because elements such as like carbon, sulfur, oxygen, and even like your halogens, they all tend to have even masses. Let's look at our different options. So for A, we have this benzene ring, and then NH2. So therefore this is odd, since there's one nitrogen. Then let's look at B. We have this kind of 5-membered ring. So this will be even, since there are 2 nitrogens in the compound. Okay, so let's draw out C. And we have 1, 2, 3 carbons, 1 nitrogen, another nitrogen, and then a doubly bonded nitrogen. So since this has 1, 2, 3, 4, this is even. Then let's look at D. It's another amino acid. And we have 1, 2, 3, 4 carbons. So this is another even, since there are 2 nitrogens. And then lastly, for E, let's draw this out. You count out all the nitrogens here. We have 1, 2, 3, 4, 5. So therefore this is odd. And then we can say molecules A and E will have an odd numbered molecular ion. Okay, so let's check out the answer from our junior tutor. Molecules with the total electron count becomes odd, A and E, as they contain odd number of nitrogen atoms. Solution is correct. Okay, so let's go to question number 7. In which direction will the net reaction proceed for each of these sets of initial conditions? So we have a condition where all of the concentrations are the same. And then for B, we have the same pressure for X and Z, but a different pressure for Y. Okay, so I'm going to write down the net reaction. X plus Y is in equilibrium with Z. Then Kp equal to 1 atmosphere. Oh, it's just 1, sorry. At 300 Kelvin. So the first thing I'm going to do is calculate delta N. And to do that, it's going to be the number of moles of your products minus number of moles of your reactants. And then it's going to be 1 minus 1 plus 1. So delta N is equal to -1. Okay, so for part A, first we need to calculate the value for Kc. So this is the equilibrium constant for the concentrations. So then to solve for Kc, I'm going to use the following equation, where Kp, so the equilibrium constant for the pressure, is equal to Kc times RT to the power of delta N. So I know that Kp is equal to 1. Kc is what we are trying to solve for. And then in the brackets, I'm going to use the R constant, 0.0821 liters times atmosphere over mole times Kelvin. So there's a lot of different R constants out there, so make sure you use the right one. So for instance, I'm using this value for R because of the units it's in. So for T, I put in my 300K. And then all of this to the power of -1. Okay, so now let's solve for Kc. If we try to simplify this expression, then we get the following. Okay, so you'll see our ATM cancels out. And the Kelvins cancel out as well. Then our Kc value is then equal to 24.63 at equilibrium. So now that we have Kc, the second part of part A is that we need to calculate the value of Q. So basically the reaction that is not present in equilibrium is equal to Q. And basically Q is equal to the concentration of your product over the concentration of your reactants. So I'm just going to plug in the concentration values so they all equal 1. So this gives us a Q value of 1 for QC. So since QC is less than KC, then that means the reaction will go to the right. Okay, so that was for part A. Now let's look at part B. So this is 7B. We're going to do something similar, except this time let's calculate for QP since KP is given. So QP is the pressure of your products over the pressure of your reactants. So it's going to be 1 over 1 times 0.5 and then you should get a QP value of 2. So if we know that KP is equal to 1, then that means QP is greater than KP. So therefore this reaction will go to the left. Okay, so let's see what our junior tutor said. Ooh. Okay. First, let's define equilibrium constant for any species. So that relates product and reactants distribution. It is similar to a ratio. So first they calculated A at equilibrium. They found the Q for concentrations. And then they calculated for KC. Let me go back to my page. 24.6. Yep. And then they wrote down all the different types of scenarios that you could get. Since 1 is less than 24.6, Q is less than K. Therefore, expect reactants to form more products in order to achieve equilibrium. So reaction will go to the right, basically. And then for part B, they calculated KP, or QP, I mean, and got 2. So QP is greater than KP. This has much more products than reactants. Therefore, expect products to form more reactants in order to achieve equilibrium. So the reaction will go to the left. So this solution is correct. Okay, so let's check out question 8. Classify each of the following as an electrophile or a nucleophile. Let's write down these definitions. So for electrophile, this literally means electron loving. And electrophiles have the following attributes. They are electron pair acceptors. They also have empty orbitals. And then just make like a table. And put nucleophiles on this side. So nucleophile means like nucleus loving. So basically these are electron pair donors. And they also have non-bonding electrons, typically. Okay, so now that we know the definition for these, let's sort out which ones are nucleophiles and which ones are the electrophiles. So for NH3, you can see that there is a lone pair on the nitrogen. So therefore, this is a nucleophile. And then let's look at OH minus. So because it has a negative charge plus a lone pair, it is also a nucleophile. And finally, H2O is also a nucleophile as well. H3O plus has a positive charge. So let's write it out. So therefore, it is an electrophile. And then I'm just going to draw out this methylbromine. If you break this bond right here, then the carbon will carry a positive charge. So that's why this is also an electrophile. So typically bromine, chlorine, like they're all good leaving groups. So after the bromine leaves, then that's why that carbon will have a positive charge, making it an electrophile. Let's see the answer from our junior tutor. Electrophiles, H3O plus, and then the CH3Br. Nucleophiles, NH3, OH minus, H2O. Explanation. Compounds having positive charge are called electrophiles, yeah? Compounds having lone pair of electrons and negative charge are called nucleophiles. So I'm just going to also add some of my definitions as well, just in case there aren't lone pairs involved, just in case there aren't any charges involved. I'm also going to put that electrophiles are also electron pair acceptors. And they can have empty orbitals as well. Then I'm going to add that nucleophiles are electron pair donors. And they can also have non-bonding electrons. Okay, but this solution is still correct. Okay, so I think we have room for one more quick question. Label each reactant and product in this reaction as a Bronsted acid or base. Okay, so let me write down the definition of a Bronsted acid. So Bronsted acids are proton donors. H+. And Bronsted bases are proton acceptors. So let's look at the reaction that they gave us. We have methanol plus a hydroxide ion in equilibrium to a deprotonated methanol plus water. Okay, so already we can see that our methanol was the one that donated its proton to the OH-, making this the Bronsted acid. And our hydroxide ion is the Bronsted base. And then the deprotonated methanol becomes our conjugate base. And then that leaves water to be our conjugate acid. Okay, so look at the answer from our junior tutor. Okay, so they kind of said it right here. I don't know where they got the other options from, since I only see the one. So technically this answer is correct. I'm just going to specify solution is correct. Then just put in brackets number 3 corresponds to question. Okay. So that's all the time that we have for today. So if you enjoyed today's Q&A and you'd like to be notified of when we do this next, then check out the subscribe button and also click on the notification bell if you haven't already done so. Then if you like this video, then go ahead and give it a thumbs up and leave a comment. And if you'd like to submit a question of your own, then check out the links in the description below. Also, if you wanted to share this video with all your friends and classmates if they needed any help with chemistry. So this has been Donna from OneClass, and I hope to see you soon. Bye!